And the thing is, if you contract the gas cloud just a little bit, you'll increase the gravity, but you'll increase the gas pressure even more. So it re-expands. We say these things are stable against collapse. Early in the 20th century, probably in the 1920s, a very famous astronomer named Sir James Jeans looked at this problem, did some computations, and he derived what we call the Jeans length, still established science in our field. And the idea is if a gas cloud for a given composition and size and temperature, density and temperature, is of a certain minimum size, then gravity can take over and contract it all the way down to form a star. But you got to get the gas cloud down to that point. As far as I know, all the gas clouds we've looked at, we're able to detect and measure, are many orders of magnitude too big. When I say an order of magnitude, it's a factor of 10. We're talking like millions of times bigger. So you've got to collapse this thing down and get it down to the Jeans length so that gravity can take over.
You know, I really wonder how much research Danny Faulkner, the person who was speaking in the clip I showed, did before he came to the conclusion that astronomers have never seen a gravitationally unstable gas cloud. Did he read a paper about star formation in the peer-reviewed literature? Did he read a textbook about star formation? Did he spend 5 minutes reading the Wikipedia article on star formation? Did he Google observe gas clouds that are gravitationally unstable? Well, apparently he didn't do any of that, because what he said, that astronomers have never observed a gas cloud that's gravitationally unstable, is one of the most asinine things that I've ever heard from someone who has a PhD in astronomy, as Danny Faulkner does. Okay, and I'm going to show in this video why that's true. But first, let's discuss some of the properties of gas clouds. So, remember how in previous videos I showed that gas clouds are basically over-dense regions in the interstellar medium. You have a diffuse interstellar medium, and then you have a cloud that's embedded with a higher density region that's embedded in the diffuse ISM. And on the largest scales, these clouds are called the giant molecular clouds, and they have higher density regions called clumps, and within those higher density regions are called cores, or the highest density regions, peaks in the density called cores. And it's the cores that astronomers are claiming collapse directly into stars. Now, so let's take a look at a core. So if you zoom in on one of the red dots, the red dots are cores. So if you zoom in on it, the core is going to look spherical, okay, because gravity is the dominating force, and whenever gravity is the dominating force on an object, it's spherical. And so now, in the video clip, Danny Faulkner talked about Jeans length, which is given the mass density, temperature, and mean molecular weight of a gas cloud, you can calculate something called the Jeans length. And if the cloud is bigger than the Jeans length, then it will collapse. And if it's smaller than the Jeans length, it won't. But the Jeans length, the formula for the Jeans length only takes into account two forces on the cloud: gravity and gas pressure. In reality, there are 5 forces acting on a cloud, and by cloud I mean dense core. There's gas pressure, turbulence, gravity, magnetic fields, and external pressure. Okay, so we already know about gas pressure and gravity. Gas pressure is due to the random motions of the atoms, and gravity is the attractive force. Each molecule is attracted to the center of the cloud. Technically, each molecule is attracted to all the other molecules, but the net force on any molecule is, by gravity, is towards the center of the cloud. Now, there's also turbulence. So, if you think of the cloud as a fluid, at each point in the fluid, there's a fluid velocity, which is basically a wind speed and direction. And if turbulence is present, which it almost always is, turbulence corresponds to random fluctuations in the velocity field. Okay, so so when turbulence is present, there will be random fluctuations in the velocity of the gas, the fluid velocity. Okay, and that acts like gas pressure. That acts as an outward pointing force that sort of makes the cloud disperse. Then there are magnetic fields. The galaxy has a magnetic field, and it passes through the core, and the magnetic field is coupled to the core in the sense that to a certain extent, the magnetic field of the galaxy is coupled to the core, so as the core contracts, it will pull the magnetic field with it. And so the magnetic field lines will become higher and higher concentration, and so the energy of the magnetic field will increase, and that produces an outward force that counteracts the contraction. So gas pressure, turbulence, and magnetic fields act to expand the cloud. They're outward pointing forces. And then there's also external pressure. The space around the core is not a vacuum. It's filled with gas, lower density than in the core, but it's filled with gas. It's part of the clump. And so that exerts a force on the surface of the core that points inward. So these two forces, gravity and external pressure, are forces that point towards the center of the cloud, and therefore they make the cloud want to contract. And then gas pressure, turbulence, and magnetic fields are forces that point outwards. They want to make the cloud expand. Now, so we can associate an energy with each of these forces, and that helps us tell which force is dominant. The force with the most energy will be the one that's the most dominant. Okay, and so for gas pressure and turbulence, the associated energy is just the kinetic energy due to the motion of the atoms and molecules. Then the energy associated with magnetic fields is just the energy of the magnetic field that's inside the core. The energy of gravity is the gravitational potential energy, which is the amount of work that it would take to sort of pull the cloud apart, how much work you have to do against gravity. And then the external, you can derive a formula for the energy due to the external pressure, and it turns out to be the pressure times the volume, the external pressure times the volume of the core. Okay? Now, and so I give some expressions, some expressions for what these forces are. And now, so there's a more technical way to derive which forces are important and which forces are not important in a particular situation. And in fact, what you really want is you want to know under what conditions can the dense core collapse into a star. Which means, based on this picture, under what conditions is gravity and external pressure stronger than gas pressure, turbulence, and magnetic fields, so that the inward force is stronger than the outward force and the thing can collapse. All right? Now, so we can sort of define a generalization of the Jeans length and the Jeans mass to include, because the original Jeans length and Jeans mass told you, so remember the Jeans length, if you're bigger than the Jeans length, you collapse. Or if you're more massive than the Jeans mass, you collapse. But the Jeans length and the Jeans mass only included gas pressure and gravity. If you want, so we need to sort of generalize that to include the effects of turbulence, magnetic fields, and external pressure. So you can make a sort of generalized Jeans mass and Jeans length where it includes those effects. And Jeans length is not very useful. Most people talk about the mass. So there's a critical mass. You can, if you analyze these forces, you can define a critical mass such that if the mass of the cloud is greater than the critical mass, then it will collapse into a star because gravity and external pressure are stronger than gas pressure, turbulence, and magnetic fields. And if it's less than critical mass, then one of these things is strong enough to support the cloud to prevent it from collapsing under gravity and external pressure. Okay, now, so in this formula, there are, this formula involves the properties of the gas cloud. So, sigma is the velocity dispersion of the gas cloud, and that's a technical term, but it basically means what you should think of. You should think of velocity dispersion as the average speed that an atom has relative to the center of the core due to gas pressure and turbulence. Okay, because the atoms are moving around the atoms and molecules are moving around randomly. right? And so the average speed, what matters for how well this can support a star against gravity is what is the average speed of a atom or molecule relative to the center of the cloud. Okay, so that's velocity of dispersion. Then you have the external pressure. That's P sub ext, and G is Newton's constant. Then you have the magnetic field strength inside of the core. That's the B. R is the radius of the core. So, and by the way, this expression for the critical mass can be split into two terms. The first term tells you how much mass that the gas pressure and turbulence can support, given gravity and external pressure. And then the second term tells you how much mass that the magnetic field can support. And so you add them together to get the total mass that can be supported by these forces. So if you could measure, here's what we're going to do. We're going to talk about a particular giant molecular cloud called the Orion A giant molecular cloud. Okay, and it's located in the Orion constellation. It's located 1,300 light years away from Earth. It's about 50 light years long and 13 light years wide, and it has hundreds and hundreds of dense cores. Okay, now this group of scientists decided to observe the Orion A giant molecular cloud at two wavelengths. One wavelength is 1.1 millimeters, and that's emitted by dust grains. So if you look at a picture of the Orion A molecular cloud at 1.1 millimeter wavelength, then you're seeing the dust. And then also at 2.79 millimeters, which is emitted by CO molecules. And it's emitted by CO molecules where the O is oxygen 18 when it transitioned from the lowest energy, the first excited rotational state, dropping to the rotational ground state. Because remember, molecules have rotational energy levels, so you can go from if you go from the first excited rotational state to the ground state where you're not rotating, then you have to emit a photon at a wavelength 2.79 millimeters. So if you observe the cloud at that wavelength, then you're seeing the CO molecules. Okay, now, so this group, and I'll show you a picture of the Orion A giant molecular cloud at 1.1 millimeters. So this is a picture of the Orion A giant molecular cloud. It's in what you're seeing. Darker colors mean a higher intensity of, or a brighter, more energy per second coming from that particular point. So and remember, this is coming from the dust. So you're seeing a dust density basically. Darker colors correspond to higher density dust. Okay, and so you can see there's the giant molecular cloud. It's surrounded by diffuse gas. There's clumps of higher density material, and within the clumps there's cores, which are hard to see because the cores are so small. But in this panel here, they have the authors of the paper, which by the way, the paper is cited in the description box, have put a colored dot at the location of each core. Okay, and they color coded it so that blue is they color coded by mass. So like the lowest mass cores are blue, the highest mass cores are red. Now, if you observe the cores at the CO wavelength, then you can measure the mass of the core, the radius of the core, and the velocity dispersion. Okay, and so you can get the mass of the core by just basically just the intensity of light coming from the core tells you the mass. Okay. And because more mass means more radiation is being emitted, so you just count basically count how many photons are emitted from the object, and then convert it to mass. Then for the radius of you can find the radius of a core by measuring the angle along the sky between the center of the core and the edge. And since you know the distance from the core, the distance is 1,300 light years, you can use trigonometry to convert the angle to a physical distance. And then for the velocity dispersion, if you look at the spectrum, so if you look at if you break down the light coming from a core into the different wavelengths, and you measure the intensity as a function of wavelength, then you'll find that there's a peak here at 2.79 millimeters, because at that wavelength the CO molecules are emitting. But it's not infinitely sharp because of the Doppler effect. Those, if you imagine a molecule that, if you're over here, you imagine if a molecule is moving towards you when it emits the photon will be blue shifted so that we see it at a shorter wavelength than this. And then if the atom is moving away from us, then the photon it emits will be red shifted, so we see it with a longer wavelength than that. So we see, instead of seeing a bunch of photons at exactly 2.79 millimeters, we see a spread in wavelengths because of this Doppler effect. And you can convert the width of the spectral line, how spread out the photons are in wavelengths, you can convert that immediately to velocity dispersion. Now, then you also need to know you have to know the external pressure, and the way that the authors did that is they measured the number density of the gas just outside of the cores, and they measured the temperature, and you can convert that to a pressure using the ideal gas law. Then there's the magnetic field. They did not measure the magnetic field, but there are groups that you can measure the magnetic field inside of a core by using something called the Zeeman effect. And basically what that is in the absence of, sometimes in an atom you'll have a bunch of states that have the same energy when there's no magnetic field. But when you turn a magnetic field on, then the state will have each state will have a different energy. And so that will cause what would be one spectral line to split into multiple closely spaced spectral lines. And if you can measure the distance or the difference in wavelength between the spectral lines that have been split, then you can calculate the magnetic field. So there's a different paper that calculated the magnetic field that way, and I took this value from that paper, and it's cited in the description. Okay, so let's look at a particular example first. Okay, an actual dense core observation from the paper. I picked Aztec, a particular dense core called Aztec ORI 72, and they found that the mass of this core is 15 solar masses, the radius is 0.24 parsecs, and the standard, or the velocity dispersion is 0.21 kilometers per second. And we use these two things for the magnetic field and the external pressure. If you plug those into this formula, then you find that the critical mass is 7.73 solar masses. So that's the maximum mass that can be supported by magnetic fields, turbulence, and gas pressure, which of course is way less than the actual mass. The actual mass is almost 2 times higher than the critical mass, which means that in this core, there's twice as much mass as can be supported, twice as much mass as can be, the mass is generating gravity, right? So this core has 2 times as much mass, 2 times as much gravity as can be supported by these gas pressure, turbulence, and magnetic fields. So this example proves or demonstrates that Danny Faulkner is wrong when he says that there are no observed gas clouds that are gravitationally unstable. But it's actually worse than it seems for him, because he was talking about Jeans length, and he was only including gravity and gas pressure. He could have said, turbulence and magnetic fields. Basically, his criteria for collapse is too weak. because even if the gas pressure is not enough to support a gravity in a cloud, that doesn't mean it's going to collapse, because maybe the turbulence is enough and maybe the magnetic field is enough. This is really bad for him, because this shows that even if you include the effects of magnetic fields and turbulence and gas pressure, it's still the case that there's a gas cloud out there that has way more mass than is gravitationally stable. Okay? But it gets even worse because, so you might think that, well, maybe this is an anomaly, right? Maybe most or all the gas clouds in space are gravitationally stable. And this is like one that I just picked because it's the one gas cloud that's unstable, and I want to make creationists look bad. But that's not true. This group observed 235 of the cores in the Orion A using the CO wavelength, and they measured the mass, radius, and velocity dispersion of each of those cores. And they put it online. So I downloaded their data, and for each of the 235 cores, I calculated what the critical mass is using the external pressure, the same external pressure in the magnetic field as in this example, but with the observed mass, radius, and sigma. And I found that 120 of the cores have masses that are greater than the critical mass, which means in 120 of the cores, gravity and external pressure cannot be supported, cannot be opposed by gas pressure, turbulence, and magnetic fields. That's 50%. That's more than half of the cores that they observed. Okay, so there's 120 examples of gas clouds that are gravitationally unstable, just in the part of the cloud that they observed at the CO wavelength. Now, that's not an anomaly. It's a well-known fact that half of all dense cores in the universe are gravitationally unstable by about this amount, and the other half are not. So, how wrong is he to say that there are no gas clouds that are gravitationally unstable that we've observed? Well, he's so wrong because half of all gas clouds that are observed that fall into the dense core category are gravitationally unstable, and there's over 100 such cores just in a piece of the Orion A molecular cloud. But there's hundreds, thousands of molecular clouds. So there are hundreds of thousands of gas clouds in the Milky Way that are observed to be gravitationally unstable.